Okay, so next let's talk about our actual architectural lighting. So as we said before, this is where we're going to have to get a couple things going on here. So first, good architectural lighting is crucial to the performance of our everyday activities and to the appreciation of our built environment around us. So we're going to break this down into four basic categories of what we call, of how we define our lighting. First off is we have ambient lighting. This is the lighting that helps to illuminate an entire space around us. Next, we have task or local lighting. This is light that's centered down on an individual thing that we're working on. So if you want to think about like a desk lamp that puts additional light into the area where you're working to help you facilitate that more detailed task. Next, we have accent lighting. This is useful in helping to denote edges or to help highlight architectural features. And then lastly, we have decorative lighting. This is lighting that's used simply to help set mood in a space or to help influence how you feel about that space. So a good example of decorative lighting is your Christmas lights. So if we think about all of our different types of lamps that we had, here's a table that kind of pulls all of it together for us. So on the left-hand side, you've got our standard incandescent, then the halogen and the others as we go through, all the way down to our light-emitting diode. Now within this, we see our typical efficacy for these lamps. Next, we see their typical rated life. And if you look at that, a standard incandescent could be anywhere from 750 up to 2,000 hours. But if you go down to the light emitting diode, now we're up to 50,000 to 100,000 hours. So in terms of years, typically, most incandescent bulbs will last about 0.4 to 1 year. Now that's assuming that it's going to burn through about 2,000 hours per year. If we look at the light emitting diode there on that same value, it's going to last over 25 years. Next column shows off the CRIs, everything from the excellent on our standard incandescents through some of the others down to the really bad light, low pressure sodium, and then back up at the end with an 82 for those light emitting diodes. And I'll tell you, that number's getting better every day. Next, we see the color temperatures and then their characteristics in terms of how they start. So if you remember when I talked about some of those HIDs, they've got a very long start time. So in terms of minutes, some HIDs can, if it's a mercury vapor, can take 3 to 6 minutes. Or if it's a metal halide, if it's a new one, it'll take about 5 to 7 minutes. But if it's an older one, it could take 15 to 20 minutes to actually reach its full output. Another table here, I kind of like this one as well, the lamp types on the left, and then the different applications that we utilize each one of those for. And again, you have the slide, so feel free to go back to the slide or pause the video as needed here. So the other category outside of those we need to talk about is emergency and safety lighting. These are secondary lighting systems that provide kind of backup illumination or support illumination. So typically these have a power supply that runs off the normal lighting system, and then it's got a battery backup if it fails. So examples might here be this exit lighting we see on the right, or the emergency lights down here. This large case setting is where it actually holds the backup battery. So this is typically what we see. Down here, types of emergency lighting. Emergency lighting can be broken into standby lighting or emergency escape lighting. The emergency escape lighting will typically define escape routes, open areas that you can get to, or high-risk task areas that are either to be centered on or possibly avoided. And then we have another one based upon the usage of the facility. So within traditional lighting installations, there's a couple different ways that we classify the actual luminaires. Now the luminaire is the actual fixture that holds the lamp. So let's look at a couple of these. So the first off is we have a pendant. And I've got an example of that on the right. These are luminaires that typically are hanging down, and they broadcast the light in a down only. Okay? Now, this isn't always the case. We could have one that actually can do up lighting as well as down lighting, but a pendant, no matter what, is suspended from something above it. Okay? But these are used in many cases to help spread light over an entire space. At the bottom here, we have an uplight. This is a luminaire where the light is actually shielded to only spread the light in an upward fashion. So the light is going from the source up to the ceiling and being reflected back down into the space. This is a good way to help eliminate glare in a lot of situations. Next, we have downlights. So an example here on the right would be a traditional fluorescent troffer that we would see in the ceiling. And typically just the opposite of of an uplight, these typically spread light in a downward fashion only. So another example of a downlight might be this pendant example that I'm showing here. After downlighting, we have what's referred to as a high hat. This is a type of downlight that's typically recessed up into some canister-shaped luminaire, and it typically has a shielded light that will control where the light goes. On the right-hand side, I'm showing a high hat that can actually be aimed. If you think about most of your traditional can lighting, that's an example of a high hat. So high hats also can be classified with the fact that they're recessed luminaires, meaning that they actually sit within the surface that's hosting them. So if you think about most of your fluorescent troffer lights that are set in a T-bar grid ceiling, those are typically recessed, meaning the face of the light is flush with the ceiling. The opposite of this would be what we call a face mount or a surface mount. That's when the light is actually attached to the actual surface. So if you look at the bottom right, here's an example of a light that's mounted on the outside face of the wall. So this would be a surface mount. Now this type of light in particular is referred to as a sconce. These are decorative wall-mounted luminaires that provide ambient illumination as well as they could provide task or more often than not additional decorative lighting. So here we see a list of common types of luminaires. On the left-hand side, these are all the typical names that we might see for them. And then if we follow that over into the second column, it continues from indoor to outdoor, then also down to specialty. So there's a special type of lamp that we need to talk about. These are called reflector lamps. These are typically incandescent, compact fluorescent, or HIT lamps that have a built-in reflector. So do you remember back to that ellipsoidal reflective lamp, the ER bulb? That's what we were talking about. So if you look at the examples up here, you can see the one on the left. This silvery coating here, that is coated on the inside to be reflective, so all the light will only come out over this surface right here. It won't put out light in this direction. The same with this one over here. It has the high gloss silver, and we can see it here. The difference is this is a frosted bulb, this is a clear bulb. Okay? Now typically they're referred to in two types. There's an ellipsoidal or a parabolic. That refers to what the shape is right here for the actual curve of the reflective surface, whether it's elliptical or a parabolic curve. Okay? Now, along with these, there's another type of lighting we hadn't really talked about, and this is referred to as remote source lighting installations. Okay? Now, remote source lighting, or RSL, most of us are probably familiar with. This is the idea of things like fiber optics. The idea is we have a light source, and then we have some type of medium. Maybe it's a plastic tube or a glass tube that we can actually transmit the light down to help provide light over a long distance further away from the actual light source. So you can see two examples here. Now, this is usually more costly than traditional lighting, but it can provide an aesthetic appeal that we can't get by other means. So typically this is done in a lot of places to replace where we used to use neon. So one of the primary functions of our luminaires is it needs to throw light only where it's needed. So now we're going to talk about that distribution of light. So in examples, light can be directed downward for maximum use or directed to the ceilings to help reflect off and help provide more ambient light across the entire space. So on the right-hand side, you see a table here, and in that the luminaire types are listed on the left: direct, indirect, semi-direct, general fuse and general indirect, or simply a highlighting. So highlighting, think of it like a spotlight, okay? So on the right-hand side, you see the distribution that's actually produced, so how much of the light is controlled, and we can see that there. An example of this would be here. Here's an example of a high hat, or a can light as we might refer to it in industry. And so basically, depending upon how deep I set this bulb back inside the can, controls what angle is actually visible. The further back it in is, the more narrow the beam is down here. So this light here can also be shown in this lighting diagram to the left to actually show how much light is available at different angles from the center line of the bulb. Now, for those of you with experience in the KTC, you might have seen some fixtures that look like this. Most specifically, these are what a lot of the lights in our building look like. So you can see this is the exact same bulb and three different housings. Here it's set with one type of reflector, and we see this distribution. Here it's set in a broader reflector with much straighter sides though, so it's going to control and not spread as much. And then lastly, they've actually turned the light on its side with all of this reflective surface here to help force more of the light outward and be able to get a broader distribution. One thing to think about though is when you're thinking about how you're orienting your bulbs, also think about how are you going to actually change that actual bulb inside your luminaire. All right, let's talk about glare real quick. Glare is excessive brightness in our field of vision. It can cause discomfort, and if it's bright enough, it can actually cause temporary loss of vision. Okay? So some of you might have seen this, an example on the left being kind of that halo light effect that we see around street lamps at night, or you might have seen it across your computer screen. So we define glare as it's a visual sensation caused by luminance that's sufficiently greater than the luminance to which our eyes are adapted. So this would be an example of like when you're in, glare is also when it seems so bright outside after you come out from a dark room, okay? Now, within glare, we have a classification we call discomfort glare. Discomfort glare causes visual discomfort without necessarily impairing our vision. It makes it tough to see, but we can still see. A good example of that would be the discomfort glare we get from a street light, okay? Or glare in this sense where it's not masking out our whole screen, but it does make it a little difficult to do our work. Okay, now part of glare we talk about visual comfort probability, VCP. This is the rating of a lighting installation, and we expressed as a percentage of people who, when they view it at a specific location in a specific direction, would consider it to have discomfort glare. So it's basically what percentage of people would find this to be an issue. Now, how do we control glare? Well, preventing glare requires some special attention. First, how is the fixture designed and selected? How does it help control how the light is spread? And also, how is it positioned to prevent light from entering our glare zone? Well, what is a glare zone? The glare zone we typically define as any zone that's greater than 45 degrees from the direct axis of the light, so straight on. So for 45 degrees out from that, so we're looking at it from a sideways angle, we consider that glare. So now both direct glare and reflected glare are very likely to occur here, but light emitted in the glare zone typically is what we define as what causes visual discomfort. So you can see here on our example we have right here, we have a light right here. Its light is shining onto the computer screen, reflected back to the viewer. He's seeing that light at 45 greater than the light, so therefore it's having an issue. The B lamp shines straight down. B would not have much glare. C, however, shines and it's more than 45 degrees off of the center line, so therefore both A and C in this situation would be considered to have glare and cause visual discomfort. Well, how do we solve this? Well, things we can do. We can look at positioning and selecting light fixtures that don't throw light in that glare zone. So things like putting a light further up into a can to help control what the actual spread of that light is. So here you can see these lights are recessed up, and this cuts off the angle for glare to this person here. But because they have lights in this area here, they can actually get glare into their vision based upon that. Okay? So in here, this lighting is fixed for the normal glare zone, but overhead lighting that could be shining down into our eyes or off the surface of the table that we see could be causing glare to us as well. Okay, let's do a little recap here. So illuminance and luminance. We talked about these before. Illuminance is the amount of light striking our surface, while luminance is the amount of light leaving or reflected back to us, and that's how we perceive how bright an object is. Now, remember luminance, this is luminance intensity of a surface in any given direction per unit of area. All right? So we express it in two different ways. We can do candelas per unit area or lumens per unit area. Illuminance, we talk about that's the density of luminous flux striking a surface. It describes how bright a surface might appear to the human eye depending upon the reflectance of the surface. So I could have a really bright light, but if it's a low reflectance surface, I'm not going to see a lot of light coming back at me. We have to look at the appropriate units for measurement for this, and for that we use what are called foot candles and lux. So some of you might have heard foot candle before. It ties back to that image of the single candle reflecting being projected out onto that 1 foot radius sphere over a 1 square foot area. That's a foot candle. So illuminance, when we talk about it, is equal to 1 lumen of light uniformly illuminating a surface over an area of 1 square foot. So 1 foot candle equals 1 lumen per square foot. So how bright actually is that? Well, let's look at the chart that we have here. On the left-hand side, I've got 5 different conditions. On the right-hand side is its proximate illuminance in either foot candles or lux. So let's talk about this. Light cast by a full moon on a clear night. Well, that's only 0.1 foot candles or 1 lux. But most of us could actually navigate our way around based using just that moonlight. Okay? Your standard street light puts out about 1 foot candle or 10 lux. And you can see here basically lux is typically about a factor of 10 higher than most of our foot candles. Now that's not always the case. These numbers are rounded just a bit. Most workspace lighting is anywhere from 10 to 100 foot candles. The lighting we would utilize for surgery is 1,000 foot candles. And if you walk outside on a clear day with natural sunlight, you're going to see 6,000 foot candles. So technically, you could be doing surgery outside in the bright light of the sun. Problem is, you're outside and none of us want surgery outside. One quick point out here, if you look at the fact what is the level of detail we're doing on different tasks here. Street lighting, we're typically walking on the street or we're driving. And so therefore, one foot candle is enough for us to discern where's the road, where's the center line, where's the curb, enough for us to complete that task. With workspace lighting, anything from writing to drafting to other types of tasks, we have about 10 to 100, a little bit higher detail than what we've seen before. Lighting for surgery, extremely high detail. We want extremely high contrast. Very important that we get enough lighting for that, and that's why that's up around 1,000. Now, when we talk about the recommended illuminance for different types of tasks, there was different ways to do this. Historically, they basically said, what we want to do is let's give them as much light as possible so we cover every single possibility. Their thought was more light is good. Well, the problem here is that resulted in a lot of very large lighting installations, and it sucked up a lot of energy. The current thinking that we have is that we don't want too much light. Too much light is excessive. It's wasting power. Okay? It also produces heat, which we'll talk about in a few minutes. But also, it's not needed for less difficult seeing tasks. It's wasteful because of the higher investment, maintenance, and that energy cost that goes with it. So in these cases, we typically will light a space and then we'll provide additional lighting as needed for individual tasks. So now we're talking just enough light is a much better approach. So here we can see several different spaces. So on the left-hand side, the first category, we have schools, then stores. On the right, industrial, theaters, and then post offices. And you can see the recommended level of foot candles for each of these types of areas that we would be doing different types of work. Okay? So let's talk about our general design approach here. So proper design requires we have to do 2 different types of calculation. Number 1 is we have to compute the illuminance from a single point source. And that's the one we're going to center on in our class, okay? The other one is a way of computing the average illuminance levels. This is more what you would utilize a lighting engineer for, or this is what a lot of our software that computes lighting levels does for us in the background. Now you have to do this to help evaluate lighting uniformity across the space as well. So if we look here, here's different types of tasks, task positions or areas again. And we have different types of work, desk work versus working at a video display terminal. That's a computer screen. This is just an old term because our book is getting a little old here. Other types of office work and then also service areas. And you can see the recommended lighting levels for those. Again, here's a few more. So on the first ones, we had those. Now we've got garages, labs, loading platforms, storage rooms, and warehouses. Then lastly, machine and woodworking shops. Notice that we've got a little bit more light there required. Then manufacturing and process areas as well. All right, so let's talk about how do we actually calculate light loss over distance. Well, it's not too hard to figure out. All we do is we take what is the distance from the source, and then we're going to actually square that. So an example here is we see that at 1 foot away from the light source, we have 1 square foot. Now, if we continue to project those lines out as the radius increases, we get out to 2 feet. Well, 2 squared is 4 square feet. So you can see how that projects out. When we get out to 3 feet, now we're at 3 squared, which is 9 square feet. So if I want to determine what's the level of the light at those different distances, I'll take the actual illuminance level in lumens, and I will divide that by, or in this case, we can use foot candles and candela in the math on this slide. I forgot I did that. But in here, with this, we're going to take that and we simply divide it by that number. So here we've got a 360 candela source. We're using candela, so we're okay there. But the candela, if at 1 foot away, 360 divided by 1, because that's the distance squared. 1 squared is 1. 360 divided by 1, 360 foot candles. If we do it again, now we're out at 2 feet. 2 squared is 4. So 360 divided by 4, I'm down to 90 foot candles. When I get out to 3 feet, 360 divided by the 9 square feet, now we're down to 40 foot candles. So you can see how this is tapering off as we go out. And that'll be in your math that you're going to do for this chapter, and that's exactly the way that it works. Just take the source level, whether it's in candela or lumens, and take that and divide it by the distance squared to the work plane. But we have to talk about, how do I determine what distance? Well, to look at this, we have to achieve for an average illuminance across a work plane, we have to achieve a certain level of illumination at that work plane first. So examples might be, I want 15-foot candles across a lobby floor, 30-foot candles across a conference room table, or 75 on a drafting table. You see the increasing level of detail on those. So what we need to define is, what is the target illumination? What is our goal? What is our recommended level? And that's some of the stuff that we saw before. Now, that surface that we're talking about, that's the work plane. So in this example before, the floor is the work plane for the 15. The top surface of the table, about 3 feet up, is our conference room table. And then a drafting table that sits at about 4 to 4.5 feet up, that would be the other work plane, in this case here. So we can see those. So typically most tabletops or desks are about 28 to 30. I called the conference room table 36, that's okay. Or you could have a countertop or a bench, which could be anywhere from 36 to 48 inches above the floor. So if you thought about a kitchen, what would your work plane be? Well, it would probably be your kitchen counters, which would typically sit about 36 to 40 to 48 inches above the floor. Okay, now let's talk about one of those problems. Remember where we talked about the issue with the fact of, when we put these lights in, all that power I'm putting in, if it's not producing light, it's definitely, the rest of that power has to go somewhere, and it's producing heat. So historically, when we used to say more light is better, well, that just meant we were adding more heat to the building. So one thing that's come about is the power allowance standard. Now what this means is this came out and it was meant to stimulate the use of more efficient lighting and system in buildings, but also is meant as a way of reducing a building's cooling load by reducing the waste heat output from all of those lamps. So what you have to realize is, with the majority of lamps that are out there, all of the energy consumed by lighting is at some point converted into heat into the space. So what are the benefits of utilizing that efficient lighting? Well, as we said before, 20 to 25% of the electricity consumed in the US and Canada is solely for lighting. Of that, commercial, institutional, and industrial lighting, so examples, schools, industry stores, offices, warehouse, that's typically about 80 to 90% of that total lighting electricity consumption. So 80 to 90% of this 20 to 25 of the total power consumption of the US. So here's the idea. If energy efficient lighting were used in all places where it was profitable, meaning it actually had a return on investment for us, the electricity required for lighting in the US could be cut by at least 50%. Now, the way that's done in a lot of spaces is they're utilizing blended lighting applications. This is kind of what I talked about before with the current theory on how we do lighting. So the idea is that I can use one light to provide ambient lighting in the space, And then I can also use another type of light for specific tasks that require a higher level of light, or I need a higher CRI or color rendering index for. Okay, that covers all the items in my slide set for chapter 20. There is more information in chapter 20 in the book. I do recommend you read through that as you're going through your homework. Hopefully this presentation was helpful, and I appreciate all of you sitting through it, and we'll talk about how useful it was in class later. Thank you so much, and I'll talk to you guys in class when I get back.